Hello and welcome to the Minnesota Homeland Security and Emergency Management's online training course, The Basics of Radiation. In today's popular culture, we are surrounded by misinformation about the nuclear power industry and radioactivity. This misinformation plays on our fears and our imaginations. We find it in the TV shows that we watch, the books that we read, the games that we play, the movies that we go to, and occasionally sensationalized stories will even make the news. Many times, however, the information in these popular culture sources are at best one-sided and misleading, and at worst, completely false. As a result of this influence, we all have various preconceptions when it comes to radioactivity. Unfortunately, not all of our preconceptions may be correct. It is therefore the purpose of this course to present you with the facts about radioactivity, and hopefully clear up some of the possible misconceptions people may have about what radioactivity is, what it does, and how we can use it effectively and manage it safely. For the duration of this course, we will discuss the principal aspects of radiation, including what it is, its health effects, and how we can protect ourselves from radiation. As we go through this training, we will try to put it into context as to what it means for emergency workers that would be doing various jobs in the wake of an accident at a nuclear power plant. Radioactivity is all around us and can be easily measured. In fact, if a survey meter is turned on in an empty room, we can record the background radiation. Actually, everything we encounter in our daily lives contains some radioactive material, some naturally occurring and some man-made. It's in the air we breathe, the water we drink, the food we eat, the ground we walk upon, and even in the consumer products that we purchase and use. As a matter of fact, most residential smoke detectors contain a low-activity americium-241 source, and newer energy-saving light bulbs contain small quantities of promethium-147. And while less common than it once was, some brands of lantern mantles incorporate thorium-232. Such mantles are sufficiently radioactive that they are often used as a check source for survey meters. Also, some antique pottery, such as the orange or red fiestaware, are radioactive due to the presence of uranium in the glaze. And finally, food contains a variety of different types and amounts of naturally occurring radioactive materials. For example, low-sodium salt substitute contains enough potassium-40 to double the background rate of a survey meter. Because we are surrounded by radioactivity at all times, the average person receives a dose of approximately 360 millirem to 620 millirem every year. Most of this comes from radon, the colorless and odorless gas that can seep into our basements. 15% comes from external background, and another 15% comes from various medical applications. 11% of our annual dose actually comes from inside the body, while 4% comes from various consumer products and all other sources. So why is there a range in the dose from 360 to 620 millirem? The reason is due to the increased reliance on medical applications that use radiation, especially CT scans. For example, an average chest X-ray can range from about 10 to 39 millirem, while an average CT scan varies from approximately 150 to 1300 millirem. So, depending on your exposure to the medical applications that use radiation, your average dose may be closer to 360 millirem or 620 millirem. Before we talk too much about radiation and radioactivity, we need to have a discussion about the source of radioactivity, and that is the atom itself. All atoms are composed of three building blocks: the proton, the neutron, and the electron. Each of these has different sizes, different charges, and different locations within the atom. The protons and neutrons are located in the center of the atom, or nucleus, and the electrons orbit in a cloud surrounding and enclosing the nucleus. All chemical properties of an atom are due to these orbiting electrons. Within the nucleus, different ratios of protons and neutrons can exist. Some ratios are stable, such as that found in a basic hydrogen atom, while some ratios are unstable, such as those found in deuterium or tritium. When the ratios of protons and neutrons are unstable, the atoms release this excess energy in the form of radiation. So what is radiation? Well, it's energy transported away from the nucleus of an unstable atom in the form of either particles or waves. There are many different forms of radiation, ranging from very high energy to very low energy. From the standpoint of radiation protection, radiation is usually separated into two categories, ionizing and non-ionizing, to denote the level of danger posed to humans. Ionization is the process of removing electrons from atoms, leaving two electrically charged particles behind. It is these electrically charged particles that have the potential to cause damage to living tissue. Extremely low frequency, radio, microwave, infrared, visible, and ultraviolet radiation are all considered non-ionizing or low energy, whereas X-ray, gamma, and cosmic radiation are considered high energy ionizing radiation. In this presentation, we will examine the four types of ionizing radiation that we should be aware of in the context of a release at a nuclear power plant: alpha particles, beta particles, gamma rays, and neutrons. In this figure, we have a radioactive source and four different shielding materials: a piece of paper, some metal foil, a brick wall, and a glass of water. Alpha radiation is a positively charged helium nucleus emitted from a larger unstable nucleus. It is a relatively massive particle, but it only has a short range in air, about 1 to 2 centimeters, and can be absorbed completely by paper or skin. It is therefore not considered to be much of an external hazard. Alpha radiation can, however, be hazardous if it enters the body through inhalation or ingestion. As a matter of fact, radon gas is an alpha emitter, and it is for this reason that radon is such an important and harmful internal hazard. Beta radiation is an electron emitted from an unstable nucleus. Beta particles are much smaller than alpha particles and can penetrate further into materials or tissue. Beta radiation can be absorbed completely by sheets of plastic, glass, or metal, and it does not normally penetrate beyond the top layer of skin. However, large exposures to high-energy beta emitters can cause skin burns, and such emitters can also be hazardous if inhaled or ingested. Gamma radiation is a very high-energy photon, or a form of electromagnetic radiation like light, that is emitted from an unstable nucleus that is often emitting a beta particle at the same time. It can be very penetrating, and only a substantial thickness of dense materials such as concrete, steel, or lead can provide good shielding. Gamma radiation can therefore deliver significant doses to internal organs without inhalation or ingestion. And finally, neutron radiation is a neutron emitted by an unstable nucleus, in particular during atomic fission and nuclear fusion, and so therefore plays an important role in the generation of electricity at a nuclear power plant. Because they are electrically neutral, they can be very penetrating and require heavy shielding rich in hydrogens, such as water, to reduce exposures. However, because neutrons are usually produced artificially in the reactor core, they would not be a concern in the unlikely event of a release at a nuclear power plant. Unlike a biological hazard that can potentially replicate and increase as the emergency progresses, one of the fortunate aspects concerning an emergency involving radioactive materials is that it decreases or decays over time, so that the amount that we have at the beginning of the incident is the most that we will ever have to deal with. The manner in which radioactive materials decay is also very predictable. It decays in terms of half-lives. So, at time 0, we have a certain amount of radioactive material, here represented by these 8 balls stacked on top of one another. After one half-life, half of the materials have decayed, leaving, in this case, only 4 balls of radioactive material. During the next half-life, it doesn't mean that the rest of it will decay, but again, half of the radioactive material will decay away, leaving 2 balls of radioactive material. As this process progresses, half of the material will decay away by the end of each subsequent half-life. It is important to note here that the amount of radioactive material never actually reaches 0. It only approaches closer and closer to 0 as time progresses. When working around radioactive materials, there are a couple of concepts we need to keep in mind in order to adequately protect ourselves from the effects of ionizing radiation. Those concepts are exposure and contamination. Radiation exposure occurs when a person is close enough to the source of radiation to be hit by the energetic particles and waves given off by the radioactive material. And radioactive contamination occurs when radioactive material is deposited in or on an object or person. To illustrate the difference between contamination and exposure, we have placed a person next to this campfire. As he stands there, he feels its warmth and is therefore exposed to the heat being released by the fire, just as someone close to a radioactive source would be exposed to the radiation emitted from that source. When that person moves away from the fire, they no longer feel its warmth and therefore are no longer exposed to its heat, just as someone who moves away from a radioactive source would no longer be exposed to the radiation it emits. However, unlike the fire analogy, such a person would not feel any heat from the radioactive source. With an actual campfire and an open flame, there will also be smoke that is emitted. The smoke can get on your clothes and can be detected even when the fire is no longer present. This situation is analogous to radioactive contamination. Radioactive contamination stays with you and can be detected and spread even after the person leaves the area. If there were a release at a nuclear power plant, there would be various sources of contamination and exposures that we would need to be aware of. Inhalation can occur if someone is immersed in the plume and breathes in the radioactive material contained within it, resulting in contamination. Cloud shine can be a source of exposure even if the person is not immersed in the plume. If a plume containing gamma emitters is high above, the gamma rays can still shine down due to their ability to travel great distances. Similarly, ground shine can occur if the plume is deposited on the ground, resulting in exposures from the radiation it emits. And finally, the food supply. Deposited radioactive material could potentially get into our water and even be ingested by animals that we use as a source of food and food products. Because of this possibility, we have plans and procedures that address this type of scenario. These plans and procedures are reviewed and approved annually by the Federal Emergency Management Agency, or FEMA, and are exercised regularly to ensure the protection of the public and our food supply. There are two types of contamination, internal and external. External contamination may be found on the skin or the clothing and can be removed by washing with lukewarm soap and water. And then there's internal contamination. Internal contamination is contamination that is inhaled or ingested. As such, it can't be removed by simply washing with soap and water. While this makes it more troublesome, it can be removed by normal body processes, and there are also medical ways of removing it that are available to healthcare providers. To keep our dose as low as reasonably achievable when working with and around radioactivity, we need to use the principles of time, distance, and shielding. Time. In order to minimize our dose, we must spend the least amount of time in a radiation area and be sure that we clean up any contamination as quickly as possible. Distance. The further away we are from a radioactive source, the lower our exposure rate will be. More on this in the next slide. And shielding. Shielding is placing an object or shielding material between yourself and the radioactive source. In this training, we have already discussed how various radioactive particles are shielded by different materials. Now let's explore the concept of distance in a little more depth using the inverse square law. In this field, we have a barrel that will act as our radioactive source. Now, if we place a person at a certain distance from this radioactive source, he will be exposed to radiation emitted from the barrel. At this distance, his exposure can be measured and recorded. Let's mark his location with a red circle and move him further away. We can now mark his current distance to the radioactive source with a yellow circle. If we measure his current location, we will see that he is exactly twice the distance to the barrel as he was initially. We can now calculate his new exposure using the inverse square law. The inverse square law tells us that when an individual is moved 2 times further away from the source of radioactivity, their exposure will be 1/2 squared, or 1/4 the intensity it was initially. Likewise, if we move him even further away, marking his new location now with a green circle, we find that he is now 3 times further away from the barrel than he was when we first placed him at the red circle. Again, using the inverse square law, we can calculate that when he is moved 3 times further away, his exposure will be 1/3 squared, or 1/9 of the intensity it was when he was standing at the red circle. The inverse square law demonstrates nicely the importance of increasing your distance from a radioactive source in order to maximize safety and minimize potentially harmful doses of radiation. We have many different tools available to us to help keep us safe when we work around radioactive materials. One is the direct reading dosimeter, or DRD, also known as the pencil dosimeter. Minnesota emergency workers have access to two different types of DRDs that are sensitive to different levels of radioactivity. One reads between 0 and 200 millar, or 0.2 R, and the other reads from 0 to 20 R. Using these DRDs, we can keep track of our exposure in real time. By holding them up to the light and looking through them, we will see a scale with a needle telling us our current exposure. These dosimeters can be reused and re-zeroed as necessary by using a charger to reset the needle. It is for these reasons that DRDs are so convenient to use, but there is one drawback, and that is their accuracy. They are not extremely accurate, and the needle can jump if they are bumped or dropped, resulting in incorrect readings. Another dosimeter that would be used by Minnesota emergency workers is the thermoluminescent dosimeter, or TLD. These dosimeters are extremely accurate, and their readings would constitute the legal exposure received by emergency workers during an incident. Unfortunately, these dosimeters also have a drawback, and that is that they are not able to be read in real time the way DRDs can be. To read a TLD, they need to be collected and sent off to a lab to be analyzed. Therefore, emergency workers would be required to carry both types of dosimeter during an incident. The DRD, which can be read in real time, as well as the TLD, which is extremely accurate. Another instrument we can use is the Geiger counter or survey meter. These are used to detect the presence of ionizing radiation. Because radioactive contamination is invisible, we can use survey meters such as the one pictured here to find radioactive contamination wherever it might be. Emergency workers use these or similar devices for tracking the plume, measuring exposure rates in contaminated areas, and for deconning contaminated individuals. And finally, there is potassium iodide, also known as Ki. Occasionally, this pill is referred to as an anti-radiation pill. It's not. Potassium iodide only protects one organ, your thyroid, from one radionuclide, and that's radioactive iodine. Your thyroid requires iodine in order to function properly, but it can't tell the difference between the radioactive and the non-radioactive forms of iodine. As a result, it takes up and uses whatever forms of iodine happen to be present at the time. The purpose of taking Ki is to saturate your thyroid with the non-radioactive form, so that if you encounter the radioactive form of iodine, your thyroid will not be able to take it up. Within the general population, different people have varying sensitivities to radioactivity. The youngest in the population are the most sensitive, and as we age, our sensitivity to radioactivity decreases. However, even as an adult, some cells in our body are more sensitive to the damaging effects of radioactivity than others. It all has to do with how fast our cells are dividing. Those cells that replicate the fastest are the most sensitive, such as cells found in bone marrow, while those cells that replicate very slowly or not at all, such as nerve cells, are the least sensitive to the effects of radioactivity. There are 4 possible effects to cells when exposed to ionizing radiation. First, the ionizing radiation can pass through the cell without damaging it. This would obviously be the best case scenario. Second, the radiation can damage the cell, but the cell will repair itself. Third, the radiation could damage a cell, and the cell attempts to repair itself but does so incorrectly. This could lead to division errors and ultimately to an increased risk of cancer in the long term. And fourth, it may kill the cell outright. Now, we have a lot of cells and can afford to lose a few. However, the problem comes if too many cells are killed too quickly. If this happens, acute health problems can be the result. Now let's explore scenarios 3 and 4 in a little more detail. First, scenario 3. This is a result of a low amount of radiation exposure over a long period of time, which can lead to the cumulative buildup of errors in the DNA and an increased risk of cancer in the long term. This low-level exposure over a long period of time is known as chronic exposure. In scenario 4, the death of cells can result from an acute exposure to ionizing radiation or a high dose over a short period of time. Under extreme conditions, this can result in nausea, skin damage, loss of appetite, fatigue, and even death under a worst-case scenario. While it is important not to downplay the seriousness of these acute effects, it is equally important to understand that the likelihood of experiencing these symptoms after exposure to radiation is extremely low. As a matter of fact, this is one of the misconceptions that this training seeks to correct. Before we take a look at actual numbers, we need to first understand the units that are used to measure radiation: the CPM, the Roentgen, and the REM. The CPM, or counts per minute, is used as a measurement of radioactivity and contamination, and is a common setting on many survey meters. The Roentgen is a measurement of radiation in dry air and can tell you what your exposure is. Survey meters and dosimetry can measure radiation in Roentgen. And because our cells are not made of dry air, we need something that is an expression of dose in human tissue, and that is where the term REM comes in. Because gamma radiation can damage tissue regardless of whether or not it has been ingested, the conversion between Roentgen and REM with gamma is 1:1. However, because alpha emitters are only considered to be a hazard when inhaled or ingested, the conversion is not 1:1. Keeping this in mind, for the purposes of this training, 1 REM will be considered the same as 1 Roentgen. However, it is important to remember that that is not always the case. In addition, because these terms use the metric system, 1 Roentgen, or 1 R, is the same as 1,000 milliroentgen, or milli-R, and 1 REM is the same as 1,000 millirem. Now let's put this into context and look at some actual numbers. This chart gives details about the clinical symptoms that result from various doses to ionizing radiation for an untreated individual. The first column shows that from 0 to 100 REM, there are essentially no clinical symptoms. No incidence of vomiting, no affected organs. The therapy is to let people know that they will be fine because the prognosis is excellent, and nobody dies. Now, remember back to earlier in this training when we said that the dose for an average chest x-ray is 10 to 39 millirem. If we use the high end of this range and round it up to 40 millirem to make the numbers easier to work with, we will see that 40 millirem is the same as 0.04 rem. Therefore, in order to reach the equivalent of 100 rem, it would require a minimum of 2,500 chest x-rays all at once, and still there would be no clinical symptoms. Even if the full body dose were doubled to 200 rem and clinical symptoms started to appear, without any treatment at all, the prognosis is still excellent and the dose is not lethal. Between 200 and 600 rem, everyone would begin to have clinical symptoms, and without treatment, from 600 to 1,000 rem, the prognosis becomes guarded, and the lethal range begins at 1,000 rem. So even though no clinical symptoms would be expected until doses between about 100 and 200 rem are reached, you may be asking yourself, what's happening at the cellular level at these lower doses? Well, below 10 rem, there are no noticeable effects of radiation that can be detected, even with the most sensitive biological assays. That is the reason for the 3 dotted lines below the 10 rem mark on this graph. Since no changes can be detected, the exposure risks below 10 rem are unknown. Above 10 rem, however, small changes can be detected in the DNA, and these changes become more detectable as the dose increases. So what do these numbers mean in relation to a possible accident at a nuclear power plant? Minnesota workers performing emergency services and radiological events are assigned a base dose limit of 5 rem for standard response activities. This relates to a turnback limit of 1 R as read on their dosimeters. Because direct reading dosimeters are made of metal and can only read gamma radiation, there is a 1 to 5 correction factor built in for safety purposes. Therefore, a 1 R exposure reading on a dosimeter is assumed to be equivalent to a dose of 5 rem. Critical situations may, however, justify higher emergency worker dose limits to protect the people of Minnesota. Therefore, a dose limit of 10 rem is allowed for the protection of key resources and critical infrastructure, and a dose of 25 rem is allowed for life-saving activities and the protection of large populations. Keeping with the 1 to 5 correction factor, this relates to turnback limits of 2R for the protection of key resources and critical infrastructure, and 5R for life-saving activities and the protection of large populations. Local jurisdictions determine the type of response activity for the incident and use the corresponding dose limits. Permission to exceed the dose limits from the state is only required if exceeding the limit in one of the particular response activities just outlined. Also, there is no turnback limit for responders outside the 10-mile emergency planning zone, and field teams with monitoring equipment who are actively tracking the plume have an exposure rate withdrawal limit of 100 mR per hour. So let's put this into the context of a real event. This slide shows data from the actual release at the Fukushima plant in Japan. The data lets us see exposure rates on the ground at various time points following the incident from March 17th to April 17th, 2011. As time progresses, we see evidence of the radioactive decay as the area colored in red quickly disappears and the area colored in orange gets smaller. The top left panel is from March 17th through March 19th, when the exposure rates were the highest. Even at this time point, the highest exposure rate was only about 12.5 mR per hour, meaning that if an emergency worker were to stay in that area of highest radiation exposure until they reach the Minnesota turnback limit for standard response activities of 1R, they would need to remain there for a total of 80 hours, or more than 3 days, and still there would be no noticeable changes that could be detected in their cells. To sum up, radiation does not cause immediate death, sudden incapacitation, or those horrifying burns and wounds that you may have seen pictures of on the internet, except at extremely high doses. And also, the doses received during a nuclear power plant incident would be far too low to cause any acute health effects from radiation.